This physics lab focused on DC and RC circuits. The purpose of this lab was to explore circuits and current and energy conservation. Part 1 involved predicting circuit behavior based on our understanding of Ohm's law. Part 2, how to measure conventional current and potential difference in circuits. And in Part 3, we observed ohmic resistors and capacitors behavior in RC circuits. From this, relevant concepts are seen to be current and energy conservation, Ohm's law, and the loop rule. This lab did not involve coding as usual, rather it used circuit construction application, which allowed us to model various circuitry, which, along with answered questions, was our output from this lab. The general structure of this lab will be me explaining each section, answering questions in the order of the lab itself. As stated before, Part 1 involved charge conservation and energy conservation in series circuits. The image to the right was the circuit for this section with two 1.5 volt batteries and two resistors at 47 and 100 ohms. For question 1, I1 and I2 were predicted using Ohm's law, V equals IR, which leads us to find I1 and I2 being 0.02, equal because it doesn't split into nodes. If we reverse connections of the wire to the ammeter, it doesn't change the current. Further along, I replaced one of the ammeters with a voltmeter, which broke the current leading to a 0 ammeter reading. The voltmeter was 3 volts. In the table attached, I recorded the potential difference between lettered locations. Summing these values led to 0 between total potential difference. The sum is 0 due to the loop. Around a closed loop, the potential difference becomes 0 logically because energy is conserved. This energy conservation is seen in the graph below. From A to B, there's a rise in potential because of the battery's potential. Our path definition means this drops across resistors and doesn't change from wires. Current doesn't change from our voltmeter reading because it has a large resistance to limit its effect. So for part 2, this is focused on RC current. The setup included one 9-volt battery and two light bulbs, one 10, 20 ohms, and one capacitor. First observations when setting up this experiment is that after a few seconds, light would dim. This was similar even when the battery was removed and the light bulbs were connected directly to the capacitor. We found average time discharge with a 10 ohm bulb through 3 trials of charging and discharging, and they are below. And in part 3 involved a similar setup, but focused on time-dependent voltage across the discharging capacitor for RC currents. So the energy conservation equation for this circuit is the delta V of the capacitor plus delta V of the resistor equals 0, assuming that the electric field in the connecting wires is negligible. So by plotting a natural log plot of delta V divided by delta V naught versus T should yield a straight line with a slope of -1 over RC, RC being the time constant of the circuit. My results were not exactly linear, and which affected my slope value, but yeah, that would be the expected result. Closing questions for this lab. If you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter, what's different about a real one and how would it have affected the circuits you hooked it up to? With an actual ammeter, readings would be less accurate and more idealized than in this model, which are purely based off of formulaic data. Meters alter both the voltage applied to the resistor and the current flowing through it in real life. If I was doing this lab in real life and used a real battery to charge a capacitor with no real resistor in the current, it would cause the capacitor to charge instantaneously to the voltage applied to it because the resistor wasn't attached. It would reach full charge quicker, and the time to would follow this equation, delta V equals delta V naught e to the -t over RC, with RC being the time constant that we calculated before. That's all for this lab. Thank you.